Actually, it's not here, but
Check, check, 1, 2. All right.
Watch out.
Not even though CNN's here, the class was already dried up.
All right, morning, everyone. The usual stuff, please get your attendance poll done. I promised the kids in Kigali that I'd post the attendance poll number on Piazza, but I seem to have forgotten. I'll do that from the next class. It's 8 a.m. as somebody's alarm just went off. I'm not sure who said it, so let's start. First, your laptops, fill out the attendance poll, shut your laptops. Please settle down. The classroom is half empty. I don't blame the rain for this. It's just that you guys didn't turn up. Yes?
The slides aren't on the website.
The slides are not on the website? Okay, that means you're going to have to pay attention, right? Isn't that a good thing? So they were supposed to be on the website. Apparently, they haven't gone up. My TAs are not here either. So, all right, let's begin. We're going to continue our series of lectures on CNNs, convolutional neural networks. But first, we're going to talk about cats. Anybody like cats? Everybody likes cats. OK. So you won't like this story. Now, the question, where did CNNs actually, what is the genesis of the convolutional neural network model? Now, we know from the last class that, well, what is a CNN, Dhriti?
It's a
OK, and what's a convolutional neural network? The distributed network. Anybody else want to tell me what a convolutional neural network is? What is a CNN?
It's like an ML device scanning through all the.
It's a convolutional neural network is basically a multi-layer perceptron that's scanning through the input for a pattern and then combining the outputs. That's all it is, right? But that's not where we arrived at CNNs from. We arrived at CNNs from cats. So for the cat lovers amongst you, this is not a class for you. But the first the original question that was asked was, how do people see? Now, what is the neural process from the eye, forming an image, all the way to recognition to cognition? Now, much of early research was based on behavioral studies. You study the response to, behavioral judgment in response to visual stimulation. So you see these pictures. What is the picture to the top left? Anybody see it? It's a cube. What about the second picture? Third one? Fourth? Spike ball. Is there a spike ball over there?
Yes.
Yes?
It's just
Is there a cube?
a bunch of cones.
It's, is there really a dog over there? No. So this is just start. What you're seeing and what you imagine you see are very different things. I just gave you a bunch of Pac-Man pictures to the top, to the left, and you just filled in the rest. I mean, 90% of the cube is not there, but you saw the entire cube. Most of the dog is absent, but you saw the dog, right? So, Mia, the slides are not up. The slides are not up. Yeah. So this is Gestalt. The brain has an innate tendency to organize disconnected bits into whole objects. And this was what people studied for the longest time. But we still understand how the brain actually processes the images. We know what it does with the images. And for that, we have to go to the study by Hubel and Wiesel in 1959, where they studied neural correlates of vision receptive fields of the cat striate cortex. The cat striate cortex is the equivalent of the human V1. The human visual system is a classic example of why, we are not the product of intelligent design. We are the product of very unintelligent design, if we were designed at all. So if you were to build a robot, and if you were to build a camera, then would the nerves start off outside the lens and pierce their way through the lens, or would the lens be outside and the nerves go backwards, the wires? How would you do it? That's going to go backwards, right? So you'd have the lens, and then you'd have a sensor, and then you'd have a wire going out. That's not how our eye is. You have the lens, then you have the wires, then you have the sensor, so the wires have to fold back and punch a hole through your retina to go to your brain. So, not a very great idea. But then if you were going to be processing these signals one step at a time, where would the first process be? Way back at the very end of the processing unit, or closest to the sensor? Closest to the sensor, right? That's not what happens in our brain. From the eye, the signals go back here. And then as they get processed, the things keep moving forward. And so the cat's striate cortex, this is our V1 portion of the brain. The cat's striate cortex is the equivalent of the human V1. And so these guys studied the cat's striate cortex. We know that individual cells in the cat's striate cortex, or even the V1, respond to different patterns, but what are these? So here's what they did. They caught a whole bunch of cats. How many of them? 24 of them, anesthetized them, immobilized them, held their eyes open, and then ran some experiments. They don't tell us what happened to the cat afterwards, but they tell us they studied slices of their brain. So I leave the rest to your imagination, right? But here's what they did. They held the eyes open, and they beamed light of different wavelengths, a little pinpoint in the eye. They move it in different directions. And they take the reading, and took the readings of individual cells to see which patterns cause the cells to respond most. And what they found was roughly this. If this is the retina, then if you beamed light all over the retina, the cell didn't respond. Now, on the other hand, there were some regions in the retina where if you beamed light on these regions, the cell definitely didn't respond, regardless of what else happened. So these were the inhibitory regions. Inhibitory regions. And then there were other regions where if you beamed the light, the cell responded, provided there was nothing on, there was no other light on the inhibitory region. And so each cell responded to light in a specific region of the retina. This was called the cell's receptive field. And within the receptive field, you had this pattern. If you had light falling everywhere, nothing responded. If you had light falling on the inhibitory regions, it definitely didn't respond. If you had light on the excitatory region but not the inhibitory region, it responded. What was the pattern of these excitatory regions? The pictures up there show you what they found. that individual cells respond to oriented lines, basically. So the one to the top right shows you that that cell is responding to a line of this kind. Why is it a line? Because it's not just any blob. If I put a blob of light, then it's going to fall on both the inhibitory and the excitatory regions. It must fall only on the line, right? And here are more results. They take a pinpoint of light and they just keep waving it around. And the nerves actually respond with spikes. So in this particular nerve, if the light is being waved in the horizontal plane, there is no response. As you keep changing the angle, when the light is perfectly vertical, you get the most spiking, and then it goes all the way back. It's not spiking again. So what is the response of this particular cell? Anybody? What is it responding to? Can somebody say that aloud?
Vertical lines.
Which cell it's responding to vertical lines, right? Guys, can everybody say vertical lines so you wake up? 1, 2, 3.
Vertical
Thank
lines.
you, right? I need you guys to wake up, otherwise I'll send you all out for coffee. Now, and so this is what we found. They found oriented slits of light were the most effective stimuli for activating striate cortex neurons. And then in a later paper, they showed that's even more complex than that. There are structures that they call the simple cells and complex cells. And simple cells were the ones that actually had this preliminary response, and complex cells cleaned up the response of the simple cell. So how did the simple cell respond? This would be a simple cell. Each cell on the retina has a more or less circular response. It responds to light which falls within a circle around that cell. But then the simple cell itself is connected to a linear pattern of these retinal cells, which means that the simple cell is now responding to a linear pattern. But then many different simple cells would be responding to similar patterns, and these things can be easily fooled. So then the complex cells would actually operate on groups of these simple cells. And just pick up the most active of these so that incidental firings due to noise are not captured. And so the response of the complex cells was more robust than those of the simple cells. Yes, Jeffrey?
The simple cells, like linear combinations, they pull about complex cells like activations.
Not really. We will get to that, right? So, but these are cells, neurons, right? This is how the whole thing works. That makes sense? Right? Simple cells are responding to linear patterns. Complex cells are looking at groups of these guys to decide to pick up the most energetic response to make sure that you're not just capturing responses to random noise. And so complex C cells build from similarly oriented simple cells, or S cells. They fine-tune the response, and then they showed that the response of the complex cell is subsequently read by other simple cells, whose response is cleaned up by other complex cells. And so you have a hierarchical buildup of the patterns that these neurons respond to, until when you get pretty deep into the brain, they're looking at, they're recognizing complete faces and such whatnot. So they later had experiments on monkeys, and I don't want to talk about these. It's bad enough talking about cats. And to add insult to injury, they said that the model cannot accommodate color, spatial frequency, and other features to which neurons are tuned. Tragic. Okay. But here's your first book. Okay, Ivysaur. Who's Ivysaur?
Ivysaur.
Ivysaur is absent, right?
No, that's me. That's me.
Who's Pichu?
Ivysaur's on Zoom.
Yes, Pichu. Oh, what? Are you Pichu or Ivysaur?
I'm Ivysaur.
Pichu. Okay.
Simple cells find patterns and complex cells.
Okay, the first one. So S cells find the patterns, C cells clean them up, right? Okay. Now, that's what the biology told us in 1959. Now, let's fast forward by several years to 1980. This guy, Kunohiko Fukushima, he decided to computationalize it, but he also found deficiencies in it. He came up with a model called the Neocognitron. And the Neocognitron tells me that there must have been a cognitron before it, so this must have been V2 or something. But then he found that there are deficiencies in the basic model. How many of you have heard of the term a grandmother cell? Have you heard of the Jennifer Aniston neuron? No? So this is actually a paper in Nature where when you have patients of epilepsy, they have lesions on the brain. And so they go in for surgery where their brain is just opened up and they're just left there with their brains open for several days. So that's fantastic for people who work on cognition. They go and lay a whole bunch of sensors on the brain, show different stimuli to these patients, and find out which sensors fire. And they found out that in the case of one particular patient, there was a neuron that only fired when this person saw pictures of Jennifer Aniston. And so this was the famous Jennifer Aniston neuron. Nothing special about Jennifer Aniston. You have a neuron for every single person, your grandmother, for instance. And so your grandmother's cell fires if your grandmother appears into your field of vision. But that grandmother's cell fires regardless of whether grandmother's out there or out there. Just the presence of grandma is enough. And that's something that the Hubel and Wiesel model didn't quite capture. It's just saying, I need grandma to be right here for this cell to fire. So Fukushima actually sort of fixed this in a computational model. And that was the Neocognitron. He said the visual system consists of a hierarchy of modules, each comprising a layer of C cells. So in each module, you would have a layer of S cells followed by a layer of C cells. So each comprising a layer of S cells followed by a layer of C cells. And so the S cells would be capturing patterns and the C cells would be cleaning them up. Now, furthermore, how was this block arranged within, how are the cells arranged within each block? So for example, you might have the S cells were arranged in several planes. And within each plane, you had an entire arrangement of neurons. Every single neuron within a plane responded to the exact same pattern. The only difference was the position of the pattern. So if you started off with, say, the retina, then these cells over here might be looking for lines of this kind, right? So this cell will respond if the line occurs here. This cell responds if the line occurs here. Then these cells might be looking for lines of this kind, right? So this one over here would respond if the line occurred here. This one over here would respond if the line occurred here. That making sense, right? And then maybe this guy is responding to lines of this kind. And the difference between the different cells is exactly the position where they're looking for the lines. Now, each cell looks in Fukushima's model at an elliptical region to find out if the pattern that it's looking for has occurred. Subsequently, you had the C cells, and the C cell is doing exactly what the C cell did in mammalian vision. Each cell over here is looking at a set of S cell responses and somehow cleaning them up to find the best response. So the C cells, each C plane is looking at the corresponding S plane and cleaning it up. Is this making sense? Right. So this would be the first layer. Then in the second layer, these were just looking for lines, right? Now the S plane, again, is beginning to look for slightly more complex patterns. So maybe this guy consists of cells that looks for noses. If it's looking for noses, it's looking for a line of this kind, a line of this kind, and a line of this kind. So this will respond if this cell fires this guy here, finds this guy here, this cell finds this guy here, and this cell finds this guy here. All at the same time, right? Is that making sense? And so these cells are going to be actually, they'll be looking at the corresponding C cell responses, and they are simultaneously looking at all of the C cell planes to decide if the pattern that they're looking for has occurred. And then once again, these C cells are going to be cleaning these guys up. Everybody clear? Right? So that's the overall picture. You have the retina, the first layer of S cells looking for individual patterns. Within each plane, every cell is looking for the same pattern, but in a different position. The C cells are cleaning them up. Then the next layer, the S cells are looking at all of the C planes in the previous layer to look for more complex patterns, and the corresponding C plane is cleaning it up. And since it's a computational model, yes?
Are the outputs of the C's sort of like the outputs of the previous layer?
Pretty much at this point, right? And so, and because it's a computational model, he actually had formulae. So if this guy is responding to things here, it's looking at a bunch of, cell outputs here, and a bunch of cell outputs here, and a bunch of cell outputs here. How is it looking at, how is it combining them? There's this crazy formula he came up with, which actually looks a lot like a ReLU. And then how is the C cell cleaning this up? The C cell is again looking at a bunch of these guys. He came up for a formula for it, but it looks like a max, really. It looks like a ReLU, but you could replace it by a max. And so in a very simplified model, this thing is computing a weighted function of all of these guys and applying a ReLU activation to it. This thing is looking at a bunch of cells here and picking the maximum value, right? And this making sense to everybody, right? And obviously, so one of the things that happens is that when a C cell cleans up an S cell, each cell is looking at a region of the S plane. So all of this can now be skipped. The next cell is looking at the next region. And so the C planes keep getting smaller and smaller, but the number of kinds of patterns you can look for keep increasing. At the first level, you're just looking for lines. At the next level, you're looking for eyes, noses, whatnot. Then you're looking for faces, cats, and whatnot. So as you get deeper, the number of these planes keeps increasing. And he came up with a learning algorithm, Fukushima. What is the weight of this guy? So he used a simple Hebbian rule. He said this position on this C plane is being looked at by this one. It's also being looked at by this one, right? And it's also being looked at by this one over here. I'm going to pick the one that had the strongest response and ignore the rest. And then I'll just use the Hebbian learning rule on this one connection to update the weight. But once I update the weight for this cell, because all the other cells in the plane have the same response, I'm just going to copy the weight over, right? So having done that, here's what he found. That the first layer neurons actually find simple structures like lines. The second layer neurons look at more complex patterns. Like if you're looking at characters, they'd find the strokes, then they'd find portions of characters. The next layer finds full characters. The entire thing is unsupervised. There is no supervision over here, right? You're just looking at using Hebbian learning. And so he showed that if for example, on a task like digits, if you train this Neocognitron, by the time you get to the final layer, these planes each ended up capturing a different pattern. So for example, this might be capturing the digit 0. This ends up capturing the digit 1. This ends up capturing the digit 2. And it's robust to noise. If you have implicitly, you're sort of derived semantically meaningful structures in a completely unsupervised manner, which was, which kind of makes sense for how we also operate. It's a pretty good model. There's a point.
Professor, I might be sure. I don't think you heard me during poll 1. Do you think you could take this poll? Hello?
Okay, this is easy. Who's Wailord? W-A-I-L-O-R-D. Wailord is absent. Who's Zubat? Z-U-B-A-T.
I am Zubat. How are you?
Also absent.
Yes, the first one is.
Who's Granbull?
I am Zubat.
G-R-A-N-B-U-L-L.
Excuse me?
That's amazing. Yeah, okay.
Professor, I'm Zubat.
And who's Treecko? T-R-E-E-C-K-O. Okay.
Professor, I'm here. I'm Zubat.
And who's Raikou?
Professor, Zubat is here.
Absent. Who's Sunflora? Guys, we have like a 50%. So today I'm going to actually post the list of all the Pokemons who have not responded. We'll make a public post. We'll let you guys know which classes you have been absent to. Right? Yes. Okay. Who are you?
Actually, they are all on Zoom, and it seems like you have
Okay, then can you actually unmute them? Are they muted? Thank you for letting me know. Somebody. Okay, just okay, Delphine, if you're online, can you please unmute people? Right, they should not be muted. Okay.
Okay.
Does
Okay,
somebody
let me-
want to answer the first question? True. Second one, also true, right? Okay, how would you add supervision to Fukushima's model? Anybody? So this is an unsupervised model, right? There is absolutely nothing, there's no manner of supervision over here. So how would you add supervision? Yes? Yes, you would specify what patterns you're looking for, but what else do you need here? Anyone?
You need a loss function.
You need a loss function and, as yes, Alistair? Class labels and something critical is missing. What's missing here?
Classification head, like
You need a classification head. I need to finally stick a classification head on this, right? And then it can output class labels, and then yes, I can define a loss, I can have class labels, and I can train the whole thing in a supervised manner. And so we know Fukushima's model already know it works. We can just add supervision to it. And secondly, in Fukushima's model, I had all of these neurons having the same response is the same as having a single neuron scan. So that's a simple engineering change. And thirdly, in Fukushima's model, we said that each cell looked at an elliptical region of the output of the previous layer. We changed the elliptical region to a rectangular region because it's computationally more efficient, right? And other than that, we're good. So each S cell is going to be, each S plane consists of a cell scanning the output of the previous layer with a rectangular window. Each cell in each C plane consists of cells looking at a rectangular region at the output of the S plane and scanning it and picking the largest value. So here's how the S plane cells would operate. You're going to each cell this is what he won a Turing Award for. So in those days, one of the big problems, we actually had a postal service that actually delivered handwritten letters to people, and they had to understand the address. And they wanted to automate the process. So they were looking for machine learning algorithms that could do this. And this LeCun's neural network actually could do that with very high accuracy. That's the famous MNIST dataset. So the story so far, the mammalian visual cortex consists of S cells, which capture oriented visual patterns, and C cells, which perform a majority vote over groups of S cells for robustness. The Neocognitron emulates this behavior with planar banks of S and C cells with identical response to enable position invariance. Only the S cell responses are learned. The C cells are just picking a max. There's nothing to learn. Yes? Oh, the mic is not picking up? Okay. This is on. Paul?
Yeah, I hear it fine.
Okay. So something's off. All right, guys. I'm hoping this is going through, right? And LeCun's LeNet added external supervision to the Neocognitron, where the S planes of cells with identical response are modeled by a scan over the image planes by a single neuron. And the C planes are emulated by cells that perform a max over groups of S cell planes. That's it. And this gave us a convolutional neural network. So this is where convolutional neural networks came from as models of mammalian vision, as supervised models of mammalian vision. So here's the general architecture of a convolutional ConNet. I'll just call it a ConNet, right? It has say a series of convolutional and pooling layers. Convolutional layers are the analogs of the S planes in vision, and the pooling layers are the analogs of the C planes. So within each convolution layer, you're going to have a whole bunch of planes, just like in the Neocognitron, where within each plane, you're scanning the previous layer output at different positions with a single neuron, right? And then the C planes, the pooling layers also consist of a bunch of planes, where each plane is basically obtained by simply scanning the corresponding convolutional layer plane and picking the maximum value within a window. But let's actually look at this stuff in detail, right? And only the convolutional layers of the MLP are learnable because pooling doesn't really have much to learn. It's a fairly simple operation, okay? So let's see how the convolutional layer works. So a convolutional layer consists of a series of maps corresponding to the S-planes in the Neocognitron. We can call them feature maps. We can call them activation maps. Feature maps because they're looking for features. Activation maps because it's the output of some activation, right? And so within any convolutional layer, you have a bunch of these planes. Again, within each plane, you're actually plotting the output of scanning with a single neuron, right? Now, each plane, each layer, convolutional layer, is operating on the output of the previous layer, which is this guy here, right? And so each layer is operating on the previous layer. And by the way, the folks on Zoom, can you see what I'm pointing to? Yes or no? All right, if you have any issues, please, yeah, just put
No.
yes, okay. And so
no, Prof, they can't see
this,
maybe
if I consider
someone
any
zooms out.
particular plane in the convolutional layer, that plane is obtained by processing all of the planes of the previous layer simultaneously, right? So how exactly is this done? Each activation map over here, firstly, it has two components. There's an affine map, which is obtained by computing an affine function of the values in the previous layer. And then there's an activation map, which is obtained by applying an activation function to the elements in the affine map, right? So first, the affine map actually computes an operation, scans the previous layer, and computes affine functions. So that's and then there's an element-wise application of an activation function to give you the activation map. Only the affine map has weights that are learnable. The activation function, like every other activation function, is just a fixed function that operates on the affine values, okay? So now if I look at any particular convolution, let's say the one highlighted on top, that plane is going to be obtained from all of the planes in the previous layer. So what is the operation that gives me this plane? Now, instead of looking at the contributions of all of the planes of the previous layer, let me look at how one particular plane in the previous layer contributes. So how does the orange plane contribute to the computation of the highlighted yellow plane? For this, I'm going to use this example. This green picture over here represents the orange plane, which is one plane from the previous layer. The yellow, the orange box over here represents a filter that is used to derive the yellow plane from the orange plane, okay? So what we would do is place the filter on the top left corner of the previous image. So the filter values are shown in red, and the image values are shown in black. And the filter also has a bias, which I've shown you on the side, right? And so then you would perform an element-wise product over here. So you would multiply this one with this one with this 0, and so on, and then add them all up. And that sum is going to be the value that actually goes into the corresponding location of this plane. That making sense? Right? Okay. And so the computation, I got this animation of the web. The computation is going to look something like this. The filter literally scans the input, and at each position, it's performing a component-wise product, summing them all up, and storing the value. This makes sense to everybody? Zoom, any questions on Zoom? I'm not sure why Zoom is muted, but any questions on Zoom? None, right? Okay. But that just showed you what one plane in the previous layer contributed to the current plane. But we know that all of the planes in the previous layer contribute simultaneously to the computation of the current affine map, right? So I've redrawn this. This guy here represents all of the planes shown as the previous layer, meaning, remember, in a convolutional layer, we have several planes, each one obtained from one neuron scanning the previous layer outputs, right? So within any convolution layer, you're going to have a whole bunch of these planes. And so these are all the planes. And from these planes, I'm going to try to compute the affine map, highlighted in yellow. Now, corresponding to this first affine map, I will have a filter. The filter has a size. In my case, the filter size is 3 cross 3. And so if I have k maps over there, I'm going to have k of these 3 cross 3 boxes, one per map. And so the total number of parameters, weights in the filter, is going to be k times 9. All of these values can be different. That making sense to all of you? And so I'm going to place this entire filter on the collection of planes in the previous layer, perform an element-wise product, and sum them all up. And that's going to give me the element output in the first position. And then I keep repeating this operation one step at a time as I scan left to right, top to bottom, and that generates the entire output map. This is the output affine map. Any questions? Yeah.
In practice, do you like basically like some, in practice, like it looks like a square, right? So when you like slide it over like each like input map, like you get like a thingy for each of them, adding something together to get the output map.
Yeah, so because in this case, I'm only showing you 3 planes, right? But ignore the ellipses, the triple dot. So then you have 3 input planes. You have nine independent filter values. So each of those 9 independent filter values is multiplying a corresponding underlying input element. So 9 times 3, there are 27 elements that you're going to obtain. The 27 elements would all be summed up to obtain one element in the output map, right? So this is one filter. One filter is going to give you one output map. If I want a second output map, right, this is going to be looking for a different pattern. The second output map would use an entirely different filter. And so now that filter is going to be scanning the input to compute the second output map. This makes sense to everybody? Right. So here I've sort of drawn all the planes one below the other. A more common visualization is to view the whole thing as a cube. So I could just, all of these input planes, instead of plotting them one below the other, I can stack them up in the form of a cube, like I have shown over here. Then the filter, which is 3 cross 3 in my case, I can just stack all of these filter squares, one behind the other. And now they're going to form a cuboid, right? Yeah. Yes.
I have a question about like an example. Like I want to propose an example. I want to like check my understanding. So let's say we have like basically we stacked like 5 like input maps together, right?
Mm-hmm.
So what we're doing is tantamount to sliding a filter with a thickness of 5 over like that.
Yeah. And so now the filter over here is going to have, in Jeffrey's example, there will be 5 planes. If I stack them up, the cuboid is 5 deep. The filter would be 5 deep, but it would have 5 faces, each of size 3 cross 3. And then I can just put the filter on the top left corner. And then the actual filter operation is shown here. First, within the square of the filter, you would be performing an element-wise product of the filter value and the underlying element, y, and summing them up. But then it also sum across the depth of the filter. And that's going to give you a single output value on the affine map. And now this filter is going to scan left to right, top to bottom, till you fill up the entire output affine map. Does this make sense to everybody, the visualization? Right. Yes?
So in the last example, there were the 3 output maps on the previous layer, right?
Mm-hmm.
So you have 20 to generate one output map from your current layer. You need to have 27 weights, right?
Correct.
And to generate 2, you will need to have 54. Or is that not? Yeah.
So this 27 are going to generate the first map. These are going to generate the second map. So you're going to have one set of 27 for every one of the output maps, right? Right? So any questions? So one, you have to worry about a few finer, fine nitpicking details. What is the size of the output? The size of the output depends on various factors. Size of the input, the size of the filter, and the size of the output may not be identical to the size of the input. Let's see why. So consider this example. My input is size 5 cross 5. My filter is size 3 cross 3, right? So if my input is size 5 cross 5 and I don't let my filter run off the edge of the input, then how many outputs will I have? Anyone? So this is my input. I have to do this quickly before it goes back up. 1, 2, 3, 4, 5, right? And my filter is 3 cross 3. And then it's sliding, right? Each time I put it on a 3 cross 3 block, I generate one output. How many steps can I take?
9.
3, right? How did you end up with 3? So if this is n, right, n, and the first position is k, so this first position is going to give you 1. This remaining is n minus k, right, plus n minus k. And so this is how big, how wide it's going to be. This is how tall it's going to be. In our case, n was 5, k is 3, so you ended up with 3, right? And so that's basically what we got in this picture. So more in general, if I have an n cross n input and a 5m cross n filter, the output is going to be n minus m plus 1 on each side. Make sense? Right. So this means that although I'm stepping forward one step at a time, my output became smaller. What would I do if I didn't want the output to become smaller?
You pad.
I can add some zero pads, right? So in a simple convolution, an image of n cross m and a filter of m cross m is going to give you a smaller output than you want. You've lost some stuff at the edges. And so this results in a reduction in the output size, which is sometimes not considered acceptable. So how many did we lose? We went in with n. We came out with n minus m plus 1, right? So how many rows did we lose? How many columns did we lose? M minus 1, right? So this is because I got n minus m minus 1. So this is how many I lost. So I can just pad it with m minus 1 columns and rows of zeros uniformly distributed on either side of the input. And so now the output is going to be the same size as the input itself. Clear to everybody? Right, okay. So this results in an affine map. Each filter is going to give you one affine map. Then you would apply an activation function element-wise to get the final output activation map. Okay, so I have some pseudocode for just for completeness sake. Within each layer, you're scanning left to right, top to bottom. But look at what you're doing. You're pulling out a segment from all of the maps in the previous layer. And then you're just computing an inner product between the segment and your filters, which is really a filter, which is really a cube. And then you're applying an activation function to it. So for those of you who prefer to see code, this should make sense, right? Okay. So convolutional layers scan the input using a bank of filters. But then going back to the scanning MLP, a filter is just a neuron and a scanning layer. Each filter jointly scans the maps in the previous layer to produce an output map. So you're going to get as many output maps as the number of filters. And then we may have to pad the edges of the input to ensure that the output maps are the same size as the input maps, okay? So now, the other component that I showed you in the picture are these pooling layers. Because convolution layers, we said, are followed intermittently by pooling layers. Not every convolution layer has to be followed by a pooling layer. You know, you can have series of convolution layers followed by a pooling layer. But then a pooling layer must be followed by a convolution layer because stacking many pooling layers together makes no sense. It's the equivalent of having just one pooling layer, okay? So what is the pooling layer? You can perform pooling in a number of different ways. The most common pooling is max pooling. So in the pooling layer, corresponding to each input map, there's an output map. And so you would consider a window of some size. Say in my example, I have a window of size 2 cross 2. And I'd place the window on, say, the top left corner. So let's say the 4 elements here in that top corner are 3, 1, 4, and 6. You just pick the largest value as the output. Yes?
Is that why pulling it preserves its dimensions before and after, because you can't really stack anything, so just you apply the 1 4 to each map, and then you get one output map for each input map.
That's right. So the number of output maps is the same as the number of input maps, right? So and so you'd just be doing this. You'd be sliding left to right, and at each position, you're looking at all of the values within the window, and you're picking the largest value and copying it over, right? So this is basically what you do to generate an output map. Does this make sense to everybody? Right. Now, typically, you'd perform this with a stride greater than 1, generally the size of the window itself. So the output of the pooling is usually smaller than the input to the pooling. Now, so here is the pseudocode for pooling. See how I've done this? Within each window, I've stored the location of the maximum within this variable called PIDX. And then for the output, I'm just reading the value from this location. So doing this as a 2-step process rather than just picking the max is going to be important for back propagation, okay? You can, instead of pooling, you can perform max pooling. You can also perform mean pooling, where instead of taking the max, you just take the mean, and otherwise the operation is exactly the same, right? So pooling layers scan the input using a pooling operation, like selecting the max from a k cross k input block. Each pooling layer scans individual maps in the previous layer to produce an output pooled map. And for pooling, so you get as many output maps as input maps. And for pooling, we do not generally pad the edges. So the zeros may result, because if you pad edges, you have zeros, and the zeros are going to result in bogus pooled values. So you don't want that happening, right? So we've considered all the kinds of layers over here, pooling and convolution layers. Then at the very end, after the final convolution or pooling layer, we generally sort of unravel all the values into one long vector, and then you can just have a regular MLP for the final classification output. So there are a couple more operations that we like to consider. The first is the downsampling operation. What is a downsampling operation? You reduce the size of the maps. So when you reduce the size of the maps, the equivalent is this. Suppose I have a map which is like 100 cross 100, and I want to shrink it to 10 cross 10 or 50 cross 50. What would I do? I'd just be picking every second element. The equivalent of that is saying I'm making every second element 0. I'm just blanking it out. And then I'm dropping all the blanked elements. Does this make sense? Right, so this is a downsampling layer. Does it make sense to everybody, right? Okay. So it simply drops S minus 1 of S rows and columns for every map in the layer. So just the pseudocode for pulling. You're just stepping forward by how much ever you're pulling by and dropping everything in between, okay? Now, typically, so this downsampling occurs after some operations, say convolution or pulling, right? If downsampling happens with convolution, after convolution, instead of performing convolution and then performing a downsampling operation, you can combine the two and say this is the same as, yes? Downsampling reduces the size of the output. So it's just a standard operation. So long as you don't lose information, you're fine. We will get to this business of losing information in a bit, right? So there's no need to have lots and lots of redundancy. And so you make things smaller, right? So here, when I have convolution followed by downsampling, say let's say I'm performing a convolution. In a convolution, I'm always striding by 1. Then if I'm downsampling by a factor of 2, this is the equivalent of saying I'm performing a convolution, I'm scanning, but now I'm scanning with a stride of 2, right? So same thing with pooling. So downsampling, if I were downsampling by a factor of 2, I'm just going to be striding by a factor of 2. You see that the output size changes, right? So for an input of size n cross n, m cross m filters, and the stride s, the actual size, output size is going to be a floor of n minus m over s plus 1, okay? So convolution, I skip the pseudocode. Pooling, same thing. The way I showed you pooling, you're always striding by 1. But pooling is rarely done with a stride of 1. Pooling is usually done with a stride greater than 1, because if I've considered all of these elements as a group and cleaned it up, then I can skip the whole bunch because they've already been processed. And then I can go to the next one. And so pooling, downsampling after pooling is generally merged with the pooling itself to obtain pooling with a stride S. So this would be max pooling, right? That's how you perform it. So again, this is performed independently for every map. You could do the same thing with mean pooling. It doesn't matter what form of pooling you do. The point is the stride. After considering a window, now you would stride by a value that's greater than 1. That's the amount by which you want to shrink the factor by which you want to shrink the maps. Okay? So let's see the code. Now, the size of the output, changes. Anytime you're striding by a stride greater than 1, not accounting for boundary effects, then if I start off with an input map of some size, then this is going to shrink by a factor equivalent to the stride, which is exactly the same as downsampling the input by that factor, okay? The other operation we perform is upsampling. Sometimes we want to increase the size of the input. How would I increase the size of the input? So, classic thing. I get a picture. I want to make it larger. How do I make the picture larger? Lots of things we can do, but the simple, yes.
Make X copies of every row and column.
Actually, it's much simpler. I can just introduce zeros. So if I want to increase the size of the input by a factor S, then I'm going to introduce S minus 1 rows and columns of zeros between adjacent elements, and now have a larger output. Yes?
Is there a reason for choosing zeros above anything else?
Simplicity, right? Because whatever you do can be, get to that, right? So this is dilation. It's used to explicitly increase the map size. And you don't just upsample and leave the zeros in place. That makes no sense at all, right? So typically, an upsampling layer is followed by a convolution layer. And the process of convolution is going to smear the information in a manner that makes most sense. So using anything else is eventually going to give you the same thing, right? So an upsampling layer is generally followed by a convolution layer. It's not useful to follow an upsampling layer by pooling. It's just going to pick up the zeros all over the place and lose info. So whereas downsampling can be combined with both convolution and pooling, upsampling is always followed by a convolution layer, which will fill in the zeros by information drawn from the sides in the most appropriate manner, right? It's also not useful as a final layer of a CNN. So are the downsampling and upsampling layers clear to you guys, right? So I have some pseudocode for it. I'll skip it. Now, upsampling layers followed by a convolution layer are often viewed as convolving with a fractional stride. So if I'm upsampling by 2, that means I'm going to be introducing 1 row of zeros between every 2 rows, 1 column of zeros between every 2 columns, and then I perform a convolution with a stride of 1. This is the equivalent, mathematically speaking, of convolving with a stride of 0.5 because you're just increasing the size of the map. So we often use this terminology. We view it as convolving with a fractional stride, but then you must remember that it's upsampling followed by convolution. Yes, Jeffrey, you just dropped your bag.
So convolving with a stride of 1 over S is sort of like equivalent to basically inserting S minus 1 vectors on zeros between each row and column, and then performing convolution with stride 1?
That's correct.
Right.
Thank you. Yes.
In the earlier discussion, we said that we could add padding in order to prevent the image size from being changed. In downsampling, we're trying to reduce the image size. So technically, if we have a certain amount of padding and we have a certain stripe, the image size wouldn't change.
Yeah.
Would that affect the information that we're getting from it?
So adding zeros is not really going to add any information. Downsampling is going to lose information. The output won't be very different, regardless of whether you pad it with zeros or not. Now,
Why do we have to why would we do
padding is only done at the boundaries, right? So if I want to downsample and get a picture that's exactly half the size of the previous picture, I want to put some account for the boundary effects by padding with zeros and then downsample. Otherwise, it will be slightly less than half. You can think of them as independent operations, right? So map sizes can be changed by downsampling or upsampling. Downsampling drops S minus 1 of S rows and columns. Upsampling inserts S minus 1 zeros between every 2 rows and columns. And downsampling typically follows convolution or pooling. It reduces the size of the maps. Upsampling occurs before the convolution. It increases the size of the maps. It does not generally occur before pooling layers, right? So here's the story so far. And before I continue for the rest of the lecture, I'll talk about information. So the convolutional neural network is a supervised version of a computational model of the mammalian vision. It includes convolution layers comprising learned filters that scan the outputs of the previous layer and pooling layers that vote over groups of outputs from the convolution layer, right? Convolution can change the size of the output. This may be controlled via zero padding. Pooling layers may perform max, mean, p-norms. You have other kinds of pooling. Resampling layers increase or decrease the size of the map. Downsampling can be merged with the preceding operation by simply scanning with a stride greater than 1. Upsampling must always occur before convolution. Any questions? Yes. What is the use of upsampling? So I will get to that in a minute, right? We're talking about information. But first, there's a pool. Yeah. Okay. So okay, guys. It seems there's some problem with the audio in this room. So folks are speaking on Zoom, but the answer is not coming through. So I'm just going to ask you a question. If you're on Zoom, please type the answer in chat, and my TAs will read them out, right? So, okay. Who does this question go to? All right. Does anybody want to answer the first question? Okay. Togepi. Who's Togepi? You know what? We'll skip this. We'll fix the speakers. But does anybody want to answer this? Is the first statement true or false? 1 and 3. Okay. Everybody agree that 1 and 3 are the right ones? Okay. This works. Okay. And who's Rhyhorn? Rhyhorn. Is Rhyhorn on Zoom? What'd they say? 2 and 4. Is that right? Okay. So 1 and 3 and 2 and 4. Upsampling introduces S minus 1 zeros and are generally followed by convolution layers. Downsampling deletes rows and columns and are merged with the previous convolution or pooling layers. Okay. So now upsampling. Yes.
What's the main reason we are performing pooling? Like if we are doing downsampling, I understand that we are maybe getting rid of redundancy, but why are we doing pooling?
So this is, so let's say, when I have something that's looking for, say, a flower, right? It's going to be looking for something that's a petal here, a sepal here, and something here. If this guy moves by 1 pixel, does it suddenly stop being a flower? No. How do you account for the fact that you're permitting jitter of this kind? right? So you want to say, I'm going to be looking at a small region. This is my tolerance. If it occurs anywhere over here, I'm going to fire. I'm just going to copy the largest value. That makes sense?
But we're anyway scanning through the entire image. So
but if I scan, just look at this. For a flower in this position, if I would require a petal to be precisely here, right? If it moves by 1 pixel and the rest of them are in the right position, you're neither going to find the flower here nor in the next position, right?
But we're already changing the size of the image if you pool.
Once you pool, you introduce jitter and variance, yes. Then the size of the image changes. Good. Mohammed, you're answering? No, okay. So I'm not sure that answered your question.
Like, if we change the size after pooling, then the size location that we wanted of the flower doesn't remain the same.
It's going. You're introducing some invariance to position. That's about it, right? A small. So let's go back and look at this. Remember when I was scanning the entire image and I wanted to find a flower, I got a. Oh, please don't go up. Okay. I got a output at every position, right? And so then I got a bunch and then I picked the max. That told me there was a flower in the image. But for a flower, I'm looking for individual features, right? If I'm looking for a presence of a feature, then do I also want it to be sensitive to the precise location of the feature or in a region? In a region. How do you do that? We're just copying the same concept that you had at the level of the entire image to the level of the individual features, saying I'm going to check the maximum within this region. Right? Yes. Bye.
I have 2 questions. So first, like the pooling layer, like it kind of like smoothens things out, right? Like by like maxing like everything.
It doesn't smooth things out. It makes things a little more, position invariant. So just as convolution and combining the outputs made the classification position independent at the level of the pictures, once you begin distributing the patterns, then the pooling layers make the components, they make the detection of patterns invariant to variations of the individual components of the patterns.
The second question I want to ask, sir, actually, no, it's more realization. I just realized how you combine pooling with downsampling. It's because when you slide the pooling box, you slide the strike rate at 1. That's it, right?
That's it. Okay. So, any questions? So here's what happens as we go through the network, right? So let's say, is this sliding or am I imagining things? I'm imagining things, okay. So if I have an image and say the image is, say, 1024 cross 1024. I have 1,000,000 elements, right? So now I'm convolving with it with a bunch of filters. So if I convolve it with a bunch of filters, each filter, assuming that, let's assume that boundary effects are need not be considered, then each filter is going to be producing a 1024 cross 1024 map. Yes? Okay. So again, as we go through the layers, we are looking for more and more features. So you want the number of filters to keep increasing as you go through the layers. Yes or no, right? So in the first layer, you want to find edges, but then in the next layer, you want to combine them and say, want to find parts of, noses, mouths, trees, what have you. Then I want larger objects. As you go through the layers, the vocabulary increases, so you want the number of these planes to increase. But now, this guy is also, each of these is going to be 1024 cross 1024. Do I have enough information between these to reconstruct the original image? The first one is 1,000,000 entries. The second one, how many do I have?
Another 1,000,000.
1,000,000. How many do I have?
1,000,000.
So I have a total of 4,000,000 values, correct? So can I recover 1,000,000 values from 4,000,000 values? Yes or no?
Yes.
Okay, so now if I pool this, and if what is the stride I'm permitted to make sure that I still have all the information about the original image? 4? How much? So I have an overrepresentation by a factor of 4, correct? Which means each of those guys can now be shrunk by a factor of how much? 2 on each side. Is that making sense to you? Right. So if each of these now became this much, I still have 1 million values. And so I have the capacity to retain all the information about the input, except that I've distributed it into a bunch of different feature maps. Does that make sense? Okay, now suppose at the next layer, I want to have 16. Okay, let's continue. Let's say that at the next layer, I'm still going to be pooling with a stride of 2. How many maps do I need? So the next convolution is going to, what happened here? Okay, the next convolution is going to be producing a bunch of maps of the same size, right? Because this is what you're operating on, right? So, and then I pool them, they're all going to shrink in size. They'll become maybe something smaller. If I decide that my pooling is going to be performed with a stride of 2, then how many of these maps do I require to make sure that I retain everything about the original? I'm going to need 16, right? So do you see how there's an intrinsic increase in the number of features that, as you increase the number of features, you're allowed to shrink it more and more. But then as you shrink it, you also have to increase the number of features. In the limit, you're going to have just 1 million features, each of 1 pixel. And each of those is going to be capturing everything about one particular feature, how very complex feature. Does that make sense? Right. And so very often, in many models, after having decomposed this to a large number of small maps, you want to be able to go back and reconstruct the original. Now in this process, you've downsampled. Each map is small. The maps have now to be increased in size to go back and reconstruct the original. How would we do it? Upsample. That's when you begin introducing zeros and convolving to smooth things out. And you have not, so long as you make sure that the process of downsampling and computing convolutional features has not lost information, the process of upsampling and combining should give you back the input. That make sense? You look. I see a question on your face.
Well, I was just going to ask, but isn't there some information lost when we downsample?
So here's the point, right? If again, there is likely to be information loss, but if you have fewer than 1 million, there's a guaranteed information loss, right? So if I want to shrink everything by a factor of 2 on each side, I need 4 maps. At each position, I'm going to have to increase the number of maps by a factor of 4. Did that answer your question?
Yeah, I guess. So on the way back up, do we interpolate in between?
Yeah, you'd be filling in zeros and convolving. Yes, Baba.
So to ensure you don't lose information, you just adjust the number of maps?
Yes, right. Okay. Yeah.
So basically, like the number of the number of output maps you need is the number of input maps times the stride squared.
Pretty much, if you're doing 2-dimensional, convolution. Yes.
Why don't you want to retain all the information in the image? I thought the whole point was to, at the lower layers, retain the concepts. Like, this is the photo of a man instead of this pixel is this color.
Yeah, speaking of the information filter, try to get rid of things. The point is more about segregating the information and putting it in a manner where you can actually make your decisions. So you don't necessarily want to lose information, right? It's about organizing it so that you can draw linear decision boundaries. Yeah.
So to build on this question, last lecture, the reason why we wanted the scan was to motivate the position invariance. And basically this explanation you just offered the pooling isn't so much for position invariance, but rather is to crystallize each field, each feature and
So the pooling is doing, what the pooling is really doing is introducing position invariance at the sub-feature level, right? But then the process of pooling and downsampling is getting rid of redundancies as well. And so that means you can make them smaller so long as you have more maps. Yeah.
So if we want to find 1 million parameters from 5 million values, it's like an over-constrained problem, right?
Yeah.
But if we downsample it to become 1 million values and then try to find 1 million variables, we need to ensure that these equations are not correlated. Is there some sort of guarantee in the neural net?
There are no guarantees, right? Again, so this is going back to the question that we just had. Eventually, if I'm performing classification, the model is going to get rid of things that are not related to your problem itself. So there will be some loss, but we are speaking of the worst case. If I want to ensure that I'm only losing information that I really need to lose and not because of the architecture of the model itself, then you want to follow these principles, right? That answer your question? Yeah. Right. So, okay. So let's put all of these together in a typical classification task. Let's say I'm building an image classifier. You have a color image. Yes.
Does the filter size have to do with the amount of shape? Like basically, my understanding, I just had like a eureka realization about pooling, and my understanding is that like the pooling, if like a feature tends to be like in the northwest, like because in pooling it remains in the northwest, but the idea is that like where in the northwest it is like the pooling makes it a little more liberal about it, the maxes.
That's pretty much it, right? So okay, let's look at a typical image classification task. Let's say I'm trying to classify images. I'd have R, G, and B. So I have three planes. We begin introducing this term. We're going to be calling these channels, and the term channels really is drawn from images, where we call them the red channel, the green channel, and the blue channel. Now you can stack them up, right, into a cube. And so now, at the first step, you're going to have a bunch of filters. And the filters, the variables are how many filters do you use, and what is the size of the filter, the face of the filter. So if the filter is L cross L, then that's the size of the pattern it's going to be looking for, right? And typically we have the K1 is a power of 2, 2, 4, 8, 16, or whatever. Again, the size, the number of filters is governed by your willingness to lose information. If you don't want to lose information, keeping in mind that you're going to be performing pooling, you choose things accordingly, right? And then the face of the filter can be typically 5 cross 5, 3 cross 3. You're looking at really small features, or even 1 cross 1. What's 1 cross 1? I know these are small enough for fine features, particularly important for scaled down images. What on earth is a 1 cross 1 filter? A 1 cross 1 filter, is basically looking at just one element, right? When you're looking at just one element from every map, what is that? Did we encounter that in class? Yeah.
Similar to the identity activation function in MLP, like it just like calculates.
Not really. Where did we encounter this? We saw this in the last class. Before we began speaking of distributing it, it's just, if I'm scanning with an MLP, then every neuron is looking at just one pixel in the maps from the previous layer, right? So a 1 cross 1 is basically a non-distributed scan. That makes sense? There's one layer where you're not distributing the patterns any further. That's it, right? And so that would be looking at something like that. Okay, so going on, you'd start off with a bunch of filters. Each of them has a face. And so the size of the filter is going to be the size of the face times the number of input channels. The parameters to choose, how many filters, what's the size of the filters, how much do they stride by when they're computing their output, right? So that's the total number of filters. And then you also would decide whether you want to lose the size of the boundaries or not, whether you want to zero pad or not. Again, this is an engineering choice. But and then you perform your convolutions. Each filter first computes an affine map, which is simply performed by scanning the stack of input channels with the filter. And at each position, you're computing an inner product between the filter weights and the pixel values in the position where the filter is located. And so those are the Z's. We've seen the formulae before. And then we apply an element-wise activation to compute the output. And so now we are going to get, how many output channels are you going to get as a result of this? Anybody? K1, as many as the number of filters, right? And so, yeah, you're going to get as many output channels as the number of filters. Then you would perform pooling. So in a pooling, you're going to be looking at a small window. And within the window, you're going to be picking the largest element as you pool. But you don't typically perform this operation in this one step where you just pick the maximum value. You do this as a two-step process. I'll get to that first. But when you're performing pooling, the parameters to choose is the size of the pooling block and the pooling stride. And also, is it max pooling or mean pooling? Now, again, observe that pooling is performed channel by channel. On each channel, you perform pooling locally, right? And also, when you actually perform the pooling, you do this as a two-step process. First, you find the location of the maximum. You store this information. And why would you want to store this information? Pooling is a max operation. Max is and how did we compute the derivative of the max when we discussed this a couple of classes ago? Yeah.
Is it because only the max perturbs the loss?
So only the maximum value perturbs the output, right? So the derivative would only go back to the location of the max and nowhere else. And so you need to know where the derivative must be passed back. So you store the location of the max and then copy the value over from that location, okay? So that's going to be your max pooling. And so after the max pooling, you're going to get a bunch of as many channels as the number of convolutional filters, but then the channels are all going to be smaller. And then you'd have another choice again, right? By the way, filters are also often called kernels, and the outputs of the individual filters are called channels, okay? And the number of filters is the number of channels, obviously. Then you choose more filters. The number of filters with the second convolution layer does not have to be the same as the number of filters in the first layer. The number of filters really is governed largely by how much you want to shrink the maps by when you perform pooling. And so if you're going to be shrinking it by a very large factor, you want many more channels, right? And so you'd have a whole bunch of filters, which are going to generate more maps. And the parameters to choose here, again, would be the size of the filters, the number of filters, and so on. And then these are going to be, the outputs of these are going to be pooled again. So they get shrunk. And you keep, and at each point, you have parameters to choose. How many filters? What's the size of the filter? Or if I'm pooling, what kind of pooling am I performing? What is the size of the window of the pooling? And what is the stride? These are all choices we have to make. And at each point, you have to keep in mind this basic principle of loss of information. To the extent possible, you want to retain the information and let the parameters figure out what you want to lose rather than the architecture of the model itself. And then eventually you're going to have an MLP, right? So the final convolved output is fed to a softmax or a full MLP. So each convolution layer with stride 1 typically maintains the size of the image. If performed without zero padding, then it'll decrease it a bit. Each convolution layer generally increases the number of maps. And the reason we're increasing the number of maps twofold. First, as you go deeper through the network, you're looking for more and more complex features. And the number of complex features is always much greater than the number of simple features, right? And second, you also want to account for the information loss by downsampling that happens in the pooling. Each pooling layer with a stride decreases the size of the maps by a factor D. Now, the filters within a layer are typically all the same size, say 3 cross 3. But across different layers, the filters can be different sizes, right? And in general, the number of filters increases with layer. So the parameters you choose, number of convolutional and pooling layers, and the arrangement, For each convolution layer, the number of filters, the size of the filter. For each pooling layer, the spatial extent, the stride. And then for the final MLP, the number of layers and number of neurons in each layer. These are all things that we have to choose. There's a final poem. This poor person's being called a second time. Who's Sunflora? Is Sunflora on Zoom? Nope. Sunflora is not on Zoom. Who's Granbull? Granbull. Granbull is not also absent. Who's Bulbasaur? Is there a Bulbasaur?
I'm on Zoom.
Okay. Who's Surskit? S-U-R-S-K-I-T.
Surskit.
Who's Surskit? Also absent. Oma. Okay. Right. Anyways, sorry guys. So can somebody answer this question? Are they the same or not?
Yes.
Yes. Okay. So here we are, right? The number of channels in the output of a convolution layer and the number of neurons in the corresponding layer of a scanning MLP are basically the same thing. So all right, guys, shut your laptops, even if it's the final 2 minutes of class. Not allowed, okay? And so, that was the kind of network that was used by Jan LeCun for digit classification. We'll revisit this a couple of classes from now. So how do you train this thing? Training is the same as in the case of a regular MLP. The only difference lies in the structure of the network. Now we are performing convolutions, and convolutions are basically a giant MLPs with, deeply shared parameters. So you have to account for the sharing. Training, you need examples of images in the class, but again, because you're assuming position invariance, you just have to say this has a flower, this doesn't. This has a cat, this doesn't, and that's about it, right? And network parameters are trained through variance of gradient descent. Gradients are computed using backpropagation. And we will see how all of this is done in the next couple of classes next week. Any questions? Yes.
Earlier in the lecture, we said that there are two types of maps that are computed, the affine map and then the activation.
Right.
So the activation comes after the convolution or after?
The convolution computes the affine map, and then you apply the activation element-wise.
So not after the pooling.
The pooling is basically just an activation by itself, right? It's a max activation.
Okay. So we don't have like a review or anything that happens.
Yeah. And the pooling is just a max activation, right? So the story so far, convnets are supervised versions of a computational model of mammalian vision. Convolution layers comprising learned filters that scan the output of the previous layer, and pooling layers that operate over groups of output from the convolution layer to have jitter and variance. And the parameters of the network can be learned through regular backpropagation. All right? Thank you.
Yeah, am I being sore?